we've made this primary amine. We call this a primary amine. And we have lots of ammonia floating around still. And we have ethyl bromide. We have lots of these two things and a little bit of this. But at some point in time, all these ratios start shifting. We get more and more and more of this. But if we were comparing these two for this, if these two come close by to ethyl bromide, this reacts preferentially because it's a more powerful nucleophile. Has more electron density, slightly more basic than this one. All those criteria lead us to understanding that. One of the ranking questions today about nucleophiles in our quiz was about basicity and which one of those was the strongest base. It was the best nucleophile. So we have same atom, same charge, both neutral. The stronger nucleophile will be the stronger base. This one is, and I'm telling you it's stronger base now because we have the slight electron donation effect. So these two react, and what do we get from it? Well, we'll have nitrogen. These two hydrogens are in place. It's going to form a new bond to an ethyl group. There'll be a plus charge on nitrogen, and bromide leaves. Okay. This is not our final product. It's very acidic. We're in the presence of lots of amines. We have a Br minus here can pull off that proton. It doesn't really matter what pulls off that acidic proton at this point, but ultimately when we adjust the charge on this amine, we get to a secondary amine. This compound would be called diethylamine. We could name this compound diethylamine very easily. This compound stinks horribly. Okay, so we just made diethylamine in the presence of ammonia, ethylamine, and ethyl bromide, and we've just, sadly, made something that's even more nucleophilic. It's also more basic than all the amine compounds leading up to it due to this slight donation of electron density into this. It has more electrons here. It's more readily accessible to pick up an acidic proton, or if we have more electrons here, then it's more reactive towards substrates. And as you can guess, this goes on one more time. Maybe you couldn't guess it goes on one more time, but it does go on one more time. So let's actually practice this reaction one more time, and then we'll stop. But we have this in the presence of this, and at some point we get enough of this. It's a powerful nucleophile. And I'm going to skip the deprotonation step here, but there's a little step hiding in here where there's an acidic proton. We pluck it off. We get to a final neutral product. When you're studying this in your notes, you can study that step on your own. But this ends up and stops here, and you have triethylamine. It can't keep going anymore, actually, because there's no longer a proton to come off of the nucleophile. So if this attacks ethyl bromide now, it's actually more nucleophilic because it has three groups, but if it attacks ethyl bromide, it's positively charged, it's very unstable, and the reaction just goes back to this. So this particular reaction is going to stop at this particular stage, this triethylamine stage, and it's a kind of a problematic situation we're in because this wasn't really what the first example we set up on paper looked like. The first example we set up on paper looked like was ammonia, ethyl bromide, and at first glance it looks like we should have stopped at this primary amine. But as a consequence of making a primary amine, it's more nucleophilic, reacts faster, makes a secondary amine that's even more favorable to react with the substrate, and so we get to here. I'm just going to show with some data how problematic and pervasive this condition is, that these are better nucleophiles than where they came from. So people really, really were interested in trying to overcome this reaction. So even if we try to bias the reaction. So what I mean by that is, watch. If our goal is to make this particular compound from ammonia plus ethyl bromide, right? This is the goal. We've already seen there's a problem with it. But one thing you could think to try is, if we want to avoid making the secondary, tertiary, these other types of products, or the ethylamine, diethylamine, triethylamine, you might think, well, why don't we just use a lot of this? 16 equivalents or 16 molar equivalents for every mole of bromine of substrate. Right? And someone actually tried this experiment. They thought, well, I know that when I make this, it's more reactive than this. So it's liable to simply just react again and make the dye-substituted one. So what if I just shift the favor of reagents so that I just add tons and tons of this in? I'm hoping that all of these will react before this can react. And then at the end, I can just filter this off, extract this off, evaporate this off, and get rid of it. But even when this was tried, with this huge bias towards here, diethylamine was made and triethylamine was made, and these ratios were 1%, 57%, and 34%. There's some unaccounted material here for we're not going to talk about, but these were the isolated yields of these compounds. So even trying to bias this, these compounds are simply much more powerful nucleophiles than when we start with. So even if there's 16 times 10 to the 23 more molecules here, or 16 times, right, of this particular reagent, doesn't matter that these are just simply such powerful nucleophiles that even these were formed. So point of this whole thing is that making primary amines, right, if this is our goal, is problematic with SN2. So this is also kind of a problem case we have. Just going to do one more quick reaction with this, then we'll take a break. So making primary amines, like this one, very problematic. It just doesn't work. Reaction that works great, however, is if we take, we're just going to take a slightly different substrate, and if we take an amine that already has two groups on it, so this is a secondary amine, these react readily using SN2, just like we were just doing. It goes through acidic intermediate. Again, good leaving group, good substrate, reaction works no problem. This particular substrate, we can just pull off this proton with amine, with water, with Br minus, doesn't really matter. But simply if we remove an acidic proton, we can easily make tertiary amines. If we start with a secondary one, there's no complications here. The problem is if we want to stop at a secondary amine, if we want to stop at a primary amine, we get all those mixes we just talked about. But there are certain cases where not a problem. We want to make this, it's not problematic. Happens logically. This is the final resting point for nitrogen and SN2 reactions where it has three substituents in it. So we're going to use this and talk a little bit about some anti-cancer therapeutics, some chemical weapons, some cyclization reactions after our break. This nitrogen information we have here is going to be the background for that discussion we're going to have. So we're going to take a 10-minute break, 10:20 we'll resume.